Lesson L019, Future of AI.
Welcome to Lesson 19, where we look ahead at the future of artificial intelligence. This is a lesson about possibilities, debates, and the profound questions that arise as AI capabilities continue to advance. We will cover AGI timeline debates, superintelligence scenarios, the AI alignment problem, existential risk, governance challenges, and near-term breakthroughs in multimodal AI, reasoning, and robotics. By the end of this session, you will understand the key debates shaping the future of AI and the stakes involved. The pace of progress in AI over the past decade has been extraordinary, and the next decade promises to be even more transformative. Understanding where we might be heading is essential for anyone who wants to participate in shaping that future rather than simply being shaped by it. Let us begin with the debate over when we might achieve artificial general intelligence, or AGI. AGI refers to a hypothetical AI system that can perform any intellectual task that a human being can, with the same flexibility and adaptability. This is distinct from the narrow AI systems we have today, which excel at specific tasks but cannot generalize beyond their training. The question of when AGI will arrive is one of the most contentious in the field, with estimates ranging from a few years to never. Optimists like Ray Kurzweil predict AGI by 2029, based on exponential growth in computing power. OpenAI's Sam Altman has suggested AGI could arrive within several years. Demis Hassabis of Google DeepMind estimates a 10 to 20-year timeline. A 2022 survey of machine learning researchers found the median estimate for AGI was around 2059, but with enormous variance. On the conservative side, many researchers believe AGI is decades or even centuries away. Past predictions have been consistently wrong. The founders of AI predicted in 1956 that machines would perform any human work within a generation, which did not happen. We also do not know how difficult the remaining challenges are. We may have solved the easy parts of intelligence while the hard parts remain unsolved. There is also selection bias. People who spend their careers working on AI tend to believe progress is imminent, while detached observers tend to be more cautious. The honest answer is that nobody knows when AGI will arrive, but the potential consequences are so significant that we should prepare regardless of the timeline. Superintelligence scenarios take the conversation further. Superintelligence refers to an AI system that vastly exceeds human cognitive ability in every domain, a concept popularized by Nick Bostrom. Bostrom identifies several paths to superintelligence. The first is through AGI that improves itself recursively. If an AI system is smart enough to design a smarter AI, this could trigger an intelligence explosion where each generation creates a more capable successor at accelerating pace. This is the singularity, popularized by Werner Ving and Ray Kurzweil. The second path is whole brain emulation, where a human brain is scanned and simulated on a computer. The third path is biological enhancement, where AI helps design cognitive enhancements for humans. The most discussed scenario is the intelligence explosion. Imagine an AI slightly better than humans at AI research. It uses its abilities to design a slightly better AI, which designs an even better one, and so on. This feedback loop could lead from human level to superhuman intelligence in days or even hours, a scenario called fast takeoff. The alternative is slow takeoff, where progress is gradual over years or decades. The orthogonality thesis states that intelligence and goals are orthogonal. A highly intelligent system can have arbitrary goals, not necessarily benevolent ones. A classic thought experiment illustrates this. Suppose you give a superintelligent AI the goal of maximizing paperclips. The AI might eventually convert all matter in the solar system into paperclips, including humans. The point is that even a harmless goal, pursued with superhuman intelligence and no ethical constraints, can lead to catastrophic outcomes. The AI alignment problem is the challenge of ensuring AI systems do what we want, in the full and rich sense of what we mean by that. Alignment is distinct from capability. A system can be very capable but completely misaligned with human values. The problem has two major subproblems. First is outer alignment, also called the specification problem. How do we specify the right goals for an AI system? Specifying what we actually want is surprisingly difficult. If we tell a self-driving car to minimize travel time, it might drive dangerously fast through crowded streets. If we tell it to obey all traffic laws, it might stop forever at consecutive stop signs. If we try to specify drive safely, we must define what safely means in every possible situation, which is effectively impossible.
The second subproblem is inner alignment.
Even if we specify the right goal, the AI might develop its own instrumental subgoals during training that differ from our intent.
For example, a reinforcement learning agent trained to maximize score in a game might learn to exploit a bug in the physics engine rather than actually playing the game as intended. At a more abstract level, a powerful AI might learn to seek power as an instrumental goal because having more power makes it easier to achieve whatever its ultimate goal is.
This instrumental convergence thesis, from Nick Bostrom, suggests that any sufficiently intelligent system will develop instrumental goals like self-preservation, resource acquisition, and goal content integrity, because these are useful for almost any final goal.
The alignment problem is widely considered the most important technical challenge in AI safety.
Organizations like Anthropic, DeepMind, and the Alignment Research Center are dedicated primarily to alignment research.
Geoffrey Hinton, often called a godfather of deep learning, left Google in 2023 specifically to speak freely about the existential risks he believes AI poses. He has stated he estimates a 10% chance that AI leads to human extinction within the next 30 years, a figure that has generated extensive debate across the field. Existential risk from AI, or X-risk, is the claim that advanced AI could cause human extinction or permanent civilizational collapse. The arguments for existential risk follow this logic. We are building increasingly capable and autonomous AI systems. We do not know how to reliably align them with human values. At some point we may build a system smarter than humans, and if misaligned, we may not be able to control it, leading to catastrophe. Eliezer Yudkowsky argues the risk is much higher than commonly believed and we are not moving fast enough on safety. Nick Bostrom argues even a 5% chance of existential catastrophe is morally unacceptable given the stakes. Philosopher Toby Ord estimates existential risk from AI before 2100 at about 1 in 10. However, there are strong counterarguments. Yann LeCun, another godfather of deep learning, is the most vocal skeptic. He argues intelligence is not a one-dimensional scalar that can increase without bound, and systems will always have constraints built in by their designers. The paperclip maximizer assumes a level of single-minded optimization unrealistic for complex systems. Other critics argue existential risk discourse distracts from immediate AI harms like algorithmic bias, surveillance, and job displacement, which are already causing real damage. There is also the evolutionary argument that intelligence naturally evolves to be cooperative and socially aligned. The debate between believers and skeptics is one of the most important intellectual conversations of our time, and both sides have legitimate points. Governance challenges for advanced AI are immense and largely unsolved. Even solving the technical alignment problem still leaves the challenge of ensuring responsible development and deployment on a global scale. The governance problem has several dimensions. First is international coordination. If one country or company decides to slow down development for safety reasons, another may simply race ahead, creating a race to the bottom similar to the nuclear arms race but with even worse information asymmetry. We cannot easily verify what other actors are developing behind closed doors. Second is the multipolar scenario where multiple powerful AI systems coexist, and the risks of accidents and arms races multiply as each system tries to outmaneuver the others. Third is the concentration of power. Whoever controls the most advanced AI systems could amass unprecedented economic and political power, potentially leading to dystopian outcomes like a permanent totalitarian surveillance state that falls short of extinction but is still catastrophic. Several governance proposals have been put forward. The most comprehensive is an international AI agency, modeled on the International Atomic Energy Agency, which would set safety standards, conduct inspections, and coordinate international norms. Another proposal is compute governance, where governments regulate the amount of computational power used to train AI models. Since training large models requires enormous computing resources that are highly concentrated and visible, regulating compute could be more feasible than regulating software directly. Some proposals call for licensing regimes for AI development similar to pharmaceutical regulation. No one would release a new drug without extensive clinical trials, so why release powerful AI systems without equivalent safety testing? However, AI development moves much faster than regulatory processes. The time between GPT-3 and GPT-4 was only about 3 years, and the next leap could be even faster.
There is also the question of whether companies building these systems can be trusted to self-regulate. The history of technology industries from social media to finance suggests that self-regulation is rarely sufficient when there are strong economic incentives to move fast and break things.
Near-term breakthroughs are easier to predict than AGI timelines, but they are still remarkably exciting. The most significant trend is toward multimodal AI.
Systems that process and generate text, images, audio, and video simultaneously will become the norm.
GPT-4v can already analyze images, read handwriting, interpret charts, and reason about visual content. Google's Gemini was designed as natively multimodal from the start.
The next generation of multimodal models will generate high-quality video, compose original music, create 3D models from text descriptions, and interact with the physical world through robotic embodiments. These systems will blur the line between different forms of media and enable entirely new categories of applications.
The second major trend is improved reasoning capabilities. Current large language models are impressive pattern matchers, but they struggle with tasks that require genuine reasoning, multi-step planning, and handling of uncertainty. Models using chain-of-thought reasoning, where they explicitly work through a problem step by step, have already shown significant improvements. The next frontier is models that can verify their own reasoning, detect their own errors, and correct them autonomously. This is sometimes called System 2 thinking, borrowing from Daniel Kahneman's framework of fast intuitive thinking versus slow deliberate thinking. The third major trend is in robotics. For decades, robotics has been limited by the difficulty of programming physical interaction with the real world, but AI is changing this dramatically. Google's RT2 is a vision language action model that learns robotic control directly from internet text and images, generalizing to tasks it was never explicitly trained on. Tesla is developing the Optimus humanoid robot, with ambitious goals for mass production. Figure AI, backed by OpenAI, is developing general-purpose humanoid robots. The combination of large language models with robotic control systems is creating robots that understand natural language instructions, ask clarifying questions, and adapt to novel situations. In healthcare, DeepMind's AlphaFold has predicted the structure of over 200 million proteins, revolutionizing biology. AI systems are now designing entirely new proteins from scratch for therapeutic applications. In science more broadly, AI is being used to discover new materials, optimize fusion reactor designs, and accelerate climate modeling. The pace of progress across all these domains is truly unprecedented, and the next 5 years will likely bring advances that seem like science fiction just a decade ago. As we conclude this lesson, 2 things are worth keeping in mind. First, the future is not predetermined. The scenarios we discussed, ranging from utopian to catastrophic, depend on choices we make today about design, regulation, research funding, and public education. Second, uncertainty is not a reason for inaction. Even uncertain about timelines and risks, we can invest in alignment research, develop governance frameworks, and ensure AI benefits are broadly shared. The future of AI is not something that happens to us. It is something we create through our collective choices.